So in which we have calculated or we have designed the column, right? So let me show the problem first. Okay. To this problem, we have calculated the uh, what is the type of section required and whether it is suitable or the strength coming from the design section which we have designed is ISMC 350 section, sorry 300 section. So whether these two sections, channel sections, are carrying the are able to carry the load, external load of 1080 kilonewtons or not. That part we have already seen in the previous video. Okay. So now the thing is we need to calculate the space. Okay. So to this problem, the space between these two channel sections we need to calculate. So how to calculate, we'll see now. So as we have placed the channel sections like this, okay. So as this is our Z axis and Y axis, right? So this is a spacing which we have to calculate. Also, as we are having our bolts here, that means from this table you can observe this distance where we have to keep the bolts. Okay, so the gauge distance which we have written earlier. So that is the position. So this G mentioned in this picture is from this back end to the position of bolt. So I'll represent here. Okay. So as we are having our bolts here, the space between these 2 points, that means to the bolt center, this will be the gauge distance for all the bolts. Why are you telling like this? Means this is our gauge distance and this is also gauge distance. So now we have to design this column, decide the column, right? So for that, we need to equate the Ix and Iy of this entire section. Okay, so moment of inertia will be equal in both an x and y directions. So in such a way, we need to space the columns back to back. So from this equation, so Ix means here Iz, ZZ axis we are taking. So here we are having two channel sections. So I'm taking 2Iz and 2Iy. And Iz. So actually, if you observe this section, IZZ entire, I mean, if you take the channel sections individually, then their Z axis will be along the centroid. Here only this axis on, and also IZZ about the overall section. That means the jointed back-to-back spaced section with the lacing. This entire section, if you observe, that is also at the centroid only. So that means, so if you take this channel section, this ZZ axis and this ZZ axis, both are at same level. So there will not be any parallel axis theorem applied. So IZ equals to only IZ you can take, that's fine. But coming to IY, so if you observe any individual channel section that will be having y-axis here, that means about somewhere here, right? So this is also having somewhere here. But overall, if you take this section, the YY axis will be at this point. Okay, so it is having some parallel axis. So let us say this distance, right? So these are the distances for two individual columns. So now actually we need to take here the CYY value. Just, okay. So as we are calculating moment of inertia for each individual section, so here it is CYY. So this is also CYY. Okay. So the CYY value from our steel table is here they have given for ASMC 250 it is 23.6. Okay. So this will be 23.6. So for parallel axis theorem, this much distance will be calculated as a Z, means IY plus AZ square you have to consider. So IZZ will be directly taken from this channel section, which we have already written earlier. So this IZZ is 62.6 into 10 power 4. And also IYY, which we have taken for the single channel section, is 310.8 into 10 power 4. Plus area of this section, a single channel section, is 4564. And also now the Z value is here S by 2. Let me write with another thing. S by 2 plus CYY. Okay. So now S by 2 plus CYY whole square. So these two things we need to calculate. If you calculate this from this equation, CYY also we know here, only unknown will be S. So from this we can calculate the S value. So Z will be equals to S by 2 plus CYY. So here I am placing the CYY value, which is 23.6. Okay. So by equating these two, the S value which we got is 183.1 mm. So I am assuming 183.5 mm of space between those two channels. Okay. So the channels spaced, two channels placed at a spacing of 183.5 mm. This spacing is of 183.5 mm. Now, designed for the lacing system. So next step. Designed for a lacing system. So now, this is channel section. This is the lacing system. These are the bolts. Single lacing system is this one. Okay. So now the spacing between these two lacings will be calculated. That is denoted with A1. Okay. And before that, we need to assume some angle for this lacing. Okay. So this angle we can assume in between 40 to 70 degrees. So it must be in between 40 to 70 degrees. For our simplification purpose, we are assuming theta as 45 degrees. So now, for this system, I'm drawing some line diagram. Okay, so as this is one lacing and this is another lacing. So I'm naming these joints A, B, C. Now the angle here it is 45 degrees and also here is 45 degrees. That means this is theta. Okay. So from this diagram and the distance, this distance is A1. So we need to know calculate the distance between two lacings, how much the distance will be kept. So to calculate the A1 value, I am applying Pythagoras theorem. Okay. So from that, tan theta will be equals to AC by BC. Okay. So here theta is 45. So tan 45 is, as we already know that is 1. And now the distance AC we need to know. Okay. So the distance is from here to here. Okay. Yeah. The distance is from here to here. So this will include the spacing here, and also now comes the consideration of gauge distance. Why? Because this is the gauge distance to the center of the bolt we are calculating. Also this is the gauge distance and this is spacing. That means spacing and gauge distance. Previously we have taken CYY value to calculate the centroidal distance, right? So here we are going with the gauge distance G. So now the AC will be S plus 2G. So 2 times G and S. We can calculate. And this BC will be now half of this A1 distance. So it is A1 by 2, which is equals to 1, that is tan theta or tan 45, right? So by equating these two, A1 by 2 equals to S plus 2G. So now A1 equals to 2 into S plus 2G, which will be now S is 183.5 plus 2 into gaze distance is 50. So the A1 distance is 567 mm. This is the spacing between two lacings. Okay. And in next step, okay, now we need to check whether the spacing which we have provided is correct, I mean sufficient or not to avoid the buckling. Okay, so there is a check for buckling. So the check for buckling will be A1 by R minimum, which is less than 0.7 times lambda E column, and also it should be less than 50. So this is 0.7 lambda E means 0.7 times 88.9, which is equals to 62.50. Now A1 by R minimum, minimum means here Ry, just a minute, 567 divided by R minimum is 26.1. This is Ry value. Okay. So which is equals to 21.724. So it is satisfying these two conditions, right? So it is safe for buckling. So our lacing is safe. Now next step, step 7, calculate the effective length of lacing bar. To calculate the effective length of lacing bar, as we have drawn some triangle right earlier. So from this triangle, this is A1 and this is S plus 2G, A, B. Okay, so from here it is the theta value. So now if you take sine theta, the thing is we need to calculate the distance of AB. This is the length, okay, length of laced column, lacing. Okay, so now sine theta equals to AC by AB, and sine 45 is, as we already know, that 1 by root 2. 1 by root 2, and AC is S plus 2G, and AB should be our length L1. So as this is the effective length, why? Because this A and B are bolt holes. Okay. So if you see, if you observe the lacing, it will be like this. So only we are calculating the effective length, not the overall length here. So from this, as we know, all the S and G values, only unknown is L1. So now L1 is 400.92. That we, if you take 401 mm. Okay. And also now the total length will be L equals to L1 plus 2E. So L1 is the effective length, and to this if you add this edge distance, this is one edge distance and this is another edge distance. So edge distance is minimum edge distance I am taking here, which we have used in bolt calculation, that is 1.5 times the D naught. So assume diameter of bolt as 20 mm. Now hole diameter is 20 plus 2, 22 mm. So D naught will be 22 and 1.5 multiplied by 22, that is 33 mm. So here if you calculate this 401 plus 33, the total is 467 mm. Next, step 12, width and length of lacing bar. So width of lacing bar, we can calculate this from class 7.6.2. Okay, so in that we have this formula. Seven point 6.2 is here. Yeah. For width of lacing bar, there is a formula 3 times the nominal diameter of the end bolt. So we can take this width. Width is 3 times the nominal diameter is D. 3 into 20, which is equals to 60 mm. And in next step, thickness of lacing. Lacing bar, which should not be less than L1 by 40 for single lacing. So which was just located on the same page 7.6.3. Seven point three class. So this can be calculated as 401 by 40. That is equals to 10.0525 mm. So I'm taking this thickness. It should be more than this, right? So 12 mm thickness I'm taking. And next step, calculating the radius of gyration. of lacing bar. R equals to square root of I by A, which we have already known. As this lacing bar is a rectangular one, right? So for this rectangular one, IV equals to BD cube by 12 and also A equals to BD. So here the D is equals to thickness. This is thickness and this is width. This is the cross section of the lacing bar. So BT. So from this we can write this as P by root 12. So simply you can remember this formula, and the thickness is 12 by root 12, which is equals to root 12, that is 3.46 mm. And next calculation is transverse shear. As for this lacing system, the transverse shear VT will be in this direction. To calculate transverse shear from class 7.6.6.1, VT equals to 2.5% of PU. That means design load 7.6.6.1. Okay, so here it is. You can read this. So this is 2.5 by 100 into 1080 into 10 cube, which is equal to 27,000 newtons. So now F sine theta. So in this figure, if you want to calculate the forces, so axial forces will be there. So now this force we know that is Vt, right? We need to take this component, axial force component, but this is our theta. So this component will be F sine theta, right? So from this I am writing F sine theta equals to Vt by N. Right? So F equals to, here Vt is nothing but, as for these two channel sections, we are placing the lacings on two sides, right? So we can take N as 2. So now F equals to Vt by N sine theta, which is 27,000 divided by 2 into 1 by root 2. Okay, so this will give you 19091.88 newtons, that is 19.09 kilonewtons. So this is F value, that means force in the lacing bar. It is one small correction, as this is our F. So this horizontal component will be F sine theta. So we are equating these two. Okay. So now checking for the compression in lacing. Next step is checking for the compression in lacing. As our compression formula is AP into FCD, lambda lacing is L1 by R. L1 is the effective length of the lacing, that is 401, which we have calculated. So R is here 3.46 per. From I by A we have calculated, right? Minimum radius of gyration. So that is 115.89 is the lambda, which is less than 145. So this is safe. And to this 115.89, we need to take the FCD value. For lambda equals to 115.89, class FY 250 and class C. 110, for 110 it is 94.6, and for 115.89 we need to calculate, and for 120 it is 83.7. So now the FCD value is 94.6 plus 83.7 minus 94.6 divided by 120 minus 110 into 115.89 minus 110. Now FCD, which we got here, is 88.18 Newton per mm square. From the compression formula, area is BT and FCD is here, which we have calculated. B is 60 and thickness is 12, and 88.18 is the FCD value. From this, the compression force which we got is 63.48 kilonewtons, which is greater than F. So it is safe. Similarly, next step, check for tension in lacing bar. As we already know that tension formula is Ag into Fy by gamma m naught. As there is no, we don't know the net area, so directly we are taking approximate area of gross area here. Gross area is 60 into 12 multiplied by 250 is the Fy value, and 1.1 is the gamma m naught value, which I have taken from table 5. From this 63 kilonewtons we got, this is greater than force F. And if you want to design for the connection, bolted connection, for 20 mm bolt, as we have already calculated in so many problems, I am taking the direct design strength as 45.27, and number of bolts required is force in the bolt lacing system and design strength of the bolt, which is equals to 19.09 divided by 45.27. This is equals to 0.42. That means one bolt is sufficient. Okay. So this is the overall design of the lacing system. So now this is our final lacing system. Okay. So these dimensions are 60 mm and this length is calculated, and this spacing is 567, and one number of bolt is sufficient. So the final design diagram will be this one. So this is a design problem. Thank you.